Look up at the night sky on a clear evening, and what do you see? A scattering of stars, maybe the faint glow of the Milky Way stretching across the darkness. It feels vast, almost infinite. But what if I told you that everything visible to the naked eye, every star, every galaxy, is just a speck within something so incomprehensibly large it redefines the word cosmic? Welcome to the Laniakea Supercluster, a structure so immense it makes our entire galaxy feel like a single neuron in the universe's brain. Picture this: our Milky Way, with its hundreds of billions of stars, is just one of roughly 100,000 galaxies all drifting together through space, bound by gravity in an intricate web. But here's where it gets mind-bending. These galaxies aren't just randomly scattered, they're arranged in flowing streams like cosmic rivers, all converging toward a single gravitational focal point known as the Great Attractor. This isn't just a cluster of galaxies, it's a supercluster, a network so vast it spans over 500 million light-years. To put that into perspective, if the Milky Way were the size of a marble, Laniakea would stretch farther than the distance between New York and Tokyo. What makes Laniakea truly astonishing isn't just its size, it's how eerily its structure mirrors a neural network. Galaxies cluster along filaments, branching out like nerve pathways, with dense nodes where they intersect, resembling synapses firing in a cosmic mind. Scientists believe this isn't just a coincidence. The universe organizes itself in patterns that repeat at every scale, from the tiniest cells to the grandest superclusters. And if that's true, what does that say about our place in it all? Over the next few minutes, we're going to unravel the mysteries of this galactic giant, exploring how its discovery changed our understanding of the cosmos and why it might just be the closest thing we've found to the universe's own brain. Strap in, this journey is about to bend your perception of reality. To grasp the sheer scale of Laniakea, we first need to understand what a supercluster really is. Think of the universe as a vast, interconnected network where galaxies aren't isolated, they gather into neighborhoods. The smallest of these are galaxy groups, like our own local group, where the Milky Way and Andromeda orbit each other. Step up in scale and you find galaxy clusters, massive gatherings of hundreds or even thousands of galaxies bound by gravity. But superclusters, they're the metropolises of the cosmos, weaving together multiple clusters and filaments into structures so large they defy intuition. Imagine the universe's matter isn't evenly spread, it's arranged in a cosmic web, with galaxies strung along glowing threads separated by enormous voids. These filaments, some stretching hundreds of millions of light-years, intersect at dense hubs, forming superclusters. One of the most famous examples is the Sloan Great Wall, a filamentary structure nearly 1.5 billion light-years long, a staggering blueprint of how matter organizes itself on the grandest scales. But Laniakea is different. Discovered in 2014 by mapping the subtle movements of galaxies, it's not just another supercluster, it's a gravitational watershed. Every galaxy within its bounds, including our own, is flowing toward the same deep gravitational well, the Great Attractor, a mysterious region hidden behind the dust of the Milky Way. This motion reveals Laniakea's true nature, not just a random assortment of galaxies, but a dynamic, interconnected system, all drifting together like leaves caught in a cosmic current. What's revolutionary about Laniakea isn't just its size, but how it reshapes our cosmic address. Before its discovery, astronomers thought superclusters had clear boundaries. Now we see them as fluid, overlapping realms, more like continents in a gravitational ocean. Laniakea's edges blur into neighboring superclusters, suggesting the universe's large-scale structure is even more complex and intertwined than we once believed. It's a humbling reminder that even the mightiest structures in existence are just threads in a tapestry far grander than we can yet comprehend. The story of Laniakea's discovery reads like a cosmic detective novel where the clues weren't hidden in light, but in motion. For decades, astronomers noticed something peculiar. Galaxies weren't just drifting apart due to the universe's expansion. They were also being tugged sideways as if caught in an invisible current. This mystery led a team led by astronomer Brent Tully to embark on an ambitious project in 2014, using a groundbreaking technique that transformed how we see the cosmos. Instead of just mapping galaxies' positions, they tracked their velocities, the subtle shifts in their movements caused by gravity's pull. It was like listening to the universe's whisper, deciphering the silent language of celestial motion. Their method was revolutionary. Imagine trying to map a city's subway system by watching how commuters flow between stations. Tully's team did something similar but on a galactic scale. By analyzing the trajectories of over 8,000 galaxies, they noticed a pattern. Entire swaths of space were moving in unison, flowing toward a common gravitational center. These cosmic currents traced out filaments and intersections, revealing a structure so vast it had been invisible until then. The result, a first-of-its-kind map that didn't just show where galaxies were, but how they were connected, like neurons firing along the synapses of a cosmic brain. The name they chose for this colossal network, Laniakea, carries profound meaning. Derived from Hawaiian lani for heaven and akea for immeasurable, it honors both the structure's scale and the indigenous Polynesian navigators who once read the stars as their roadmap. Just as these voyagers saw the night sky as a living, connected expanse, modern astronomers now recognize Laniakea as a dynamic, ever-moving entity. It's a poetic reminder that humanity's quest to understand the heavens bridges ancient wisdom and cutting-edge science. What's truly remarkable is how this discovery upended old assumptions. Before Laniakea, astronomers defined superclusters by their density, clusters packed close together. But Tully's approach revealed a more organic truth. Superclusters are defined by motion, by the shared destiny of galaxies streaming toward the same gravitational destiny. This redefinition didn't just give us a new celestial landmark, it changed how we classify the universe's largest structures, proving that sometimes to see the bigger picture, you don't just look, you follow the flow. The cultural and scientific weight of this moment can't be overstated. Laniakea isn't just a name on a star chart, it's a testament to human curiosity's power to reveal hidden layers of reality. And yet, for all we've uncovered, the Great Attractor, the mysterious gravitational heart of Laniakea, remains obscured by our own galaxy's dust, a cosmic irony that keeps the story thrillingly unfinished. Every answer births new questions, and in that tension, science finds its most exhilarating adventures. Mapping the universe in 3 dimensions isn't just about plotting points, it's about decoding the hidden language of motion. To reveal Laniakea's structure, astronomers had to think like cosmic meteorologists, tracking not just where galaxies are, but how they're moving, the key to this breakthrough. Redshift data and peculiar velocities, 2 concepts that transformed static sky maps into dynamic portraits of cosmic flow. Redshift, the stretching of light's wavelength as objects move away from us, is astronomy's speedometer. It tells us how fast a galaxy is receding due to the universe's expansion. But galaxies aren't just drifting apart, they're also nudged sideways by gravity, creating slight deviations in their motion called peculiar velocities. These subtle shifts act like fingerprints, revealing the pull of invisible mass. Imagine throwing confetti into a windy street. While the breeze carries everything forward, you'd still see individual pieces swerve around obstacles. That's precisely how galaxies move, tracing the contours of hidden gravitational landscapes. The team behind Laniakea's discovery turned this principle into a cosmic Doppler radar. By comparing galaxies' expected redshifts based on universal expansion with their observed motion, they could calculate how much gravity was tugging them off course. This technique unveiled the Great Attractor's influence, a gravitational anomaly so powerful it's pulling thousands of galaxies, including our own, toward a point shrouded behind the Milky Way's dust. Creating this 3D map required more than just raw data. It demanded innovation. Traditional surveys plotted galaxies as dots in space, but Tully's team visualized their movements as flowing streams, using algorithms to trace the gravitational currents weaving through the cosmos. The result resembled a weather map of galactic winds, with galaxies cascading toward dense nodes like water spiraling down a drain. What made their approach revolutionary was its scale. Previous studies focused on small regions, but this team stitched together observations from thousands of galaxies, revealing patterns invisible to narrower lenses. They used radio telescopes to peer through obscuring dust, and supercomputers to simulate gravitational flows, tools that turned raw numbers into an immersive cosmic watershed. The final visualization didn't just show a static structure, it captured a universe in motion, with galaxies surfing gravitational waves toward shared destinations. This dynamic perspective redefined superclusters as living entities, their boundaries shaped by the ebb and flow of cosmic tides. It's a reminder that the universe isn't a frozen snapshot, it's a story written in the silent dance of galaxies. To truly fathom the colossal size of Laniakea, let's shrink the cosmos down to something familiar. Picture our Milky Way as a single grape about an inch across. On this scale, Laniakea wouldn't be a fruit bowl or even a supermarket aisle. It would span the length of a massive sports stadium, with galaxies packed together like an ocean of grapes filling every seat, aisle, and playing field. That's the sheer volume we're talking about, a structure so vast it dwarfs anything our everyday experiences can prepare us for. Now, let's put hard numbers to this awe-inspiring scale. Laniakea stretches approximately 520 million light-years from end to end. Wrap your mind around that distance for a moment. Even traveling at the speed of light, the universe's ultimate speed limit, it would take you 500 million years just to cross from one side to the other. Within this immensity, around 100,000 galaxies swirl together, each a city of stars in its own right. The total mass, roughly 10 to the 17th power times the mass of our Sun, a number so large it's like counting every grain of sand on every beach on Earth, then multiplying that count by millions. But here's what makes these numbers truly humbling. Laniakea isn't just big, it's a significant chunk of our cosmic neighborhood. The observable universe spans about 93 billion light-years, and while that sounds overwhelmingly large, Laniakea alone makes up roughly 1% of that total volume. Think about that, a single supercluster, just one thread in the universe's tapestry, occupies a percentage that would be negligible on a human scale, but is staggeringly vast when applied to the cosmos. What's even more mind-bending is how this scale challenges our perception of emptiness. We often imagine space as mostly void, punctuated by the occasional galaxy. But Laniakea's structure reveals a different truth. Like a sponge, the universe is full of holes, but its solid framework is more intricate and interconnected than we ever realized. Those empty voids between galactic filaments, they're not truly empty, just vastly underdressed compared to the glittering metropolises of galaxies they border. Standing back to take in Laniakea's full scope does something profound. It redefines our sense of place. We often think of Earth as a speck lost in a lonely galaxy. But zoom out further, and you see our galaxy as just one member of an immense gathering, a community bound by gravity's invisible threads. It's a perspective that's equal parts exhilarating and grounding, reminding us that even in the grand theater of the cosmos, we're part of something far larger than ourselves. At the heart of Laniakea's vast cosmic web lies a gravitational enigma so powerful it bends the paths of galaxies, the Great Attractor. Picture a force so immense it's dragging our Milky Way and thousands of neighboring galaxies toward it at 600 kilometers per second, like a cosmic whirlpool we can't escape. Yet for decades, this colossal mystery remained hidden from view, buried behind a celestial curtain known as the Zone of Avoidance, a region of space obscured by the thick dust and stars of our own galaxy's disk. It's as if we're trying to study a mountain range while standing in a dense fog, with only faint clues hinting at what lies beyond. The challenge of observing the Great Attractor isn't just about distance, it's about perspective. Optical telescopes are practically blind to this region because visible light gets absorbed by interstellar dust, but astronomers have found workarounds. Enter X-ray telescopes like NASA Chandra and Japan's Suzoku, which detect high-energy emissions invisible to optical instruments. These tools revealed something startling. Behind the Milky Way's dusty veil lies an unusually high concentration of galaxy clusters, including the Neuron cluster, a dense knot of mass acting as the Great Attractor's core. X-rays let us see the hot gas between these galaxies, mapping the gravitational scaffolding that pulls everything toward it. But here's where the plot thickens. Even when we account for the visible mass in the Neuron cluster and surrounding regions, the math doesn't add up. The Great Attractor's pull is far stronger than what observed matter can explain, pointing to the presence of dark matter, the universe's invisible scaffolding. Some theories suggest this anomaly might be part of something even larger, like the Shapley Supercluster, a monumental structure beyond Laniakea whose gravity could be amplifying the effect. Others propose that the Great Attractor isn't a single destination but a confluence of multiple gravitational currents, a crossroads where cosmic flows converge. The most tantalizing question remains, what lies deeper in the zone of avoidance? Every breakthrough peels back another layer of the mystery. Infrared surveys and radio telescopes are now probing deeper, uncovering galaxies previously lost in the glare. Each new discovery chips away at the void, revealing a universe far more dynamic and interconnected than we ever imagined. The Great Attractor isn't just pulling galaxies, it's pulling our understanding of the cosmos into uncharted territory, reminding us that some of the universe's most profound secrets are hiding in plain sight, waiting for the right tools and the right questions to bring them into focus. The cosmic web isn't just a structure, it's a pattern repeating across scales in ways that blur the line between the microscopic and the astronomical. If you've ever seen a neuron's branching form under a microscope, the resemblance to Laniakea's tangled filaments is uncanny. Both are networks where dense hubs connect through slender threads, pulsing with activity, whether it's electrical signals or the gravitational dance of galaxies. This isn't mere coincidence, it's a fingerprint of how nature organizes complexity, from the synapses in your brain to the largest structures in the observable universe. Zoom out far enough and Laniakea becomes one thread in a tapestry far grander. The cosmic web stretches across billions of light years, a labyrinth of galaxy-studded filaments intersecting at colossal knots like the Coma cluster. These intersections aren't random, they trace the invisible scaffolding of dark matter, the universe's hidden architecture. Though we can't see dark matter directly, its gravity sculpts the visible cosmos like an unseen hand pressing into dough. Galaxies aren't scattered haphazardly, they're strung along these dark matter filaments like pearls on a necklace, drawn toward the densest intersections where multiple threads converge. What's mesmerizing is how precisely this mimics neural networks. In your brain, neurons optimize efficiency by forming clusters with short, strong connections between frequently communicating regions, just as galaxies cluster along filaments to minimize gravitational commute times. Even the voids between cosmic threads mirror the empty spaces between neuron bundles. This fractal resemblance hints at universal laws of organization that transcend size, governing everything from the birth of stars to the firing of thoughts. But the cosmic web's true magic lies in its dynamism. Unlike a static spiderweb, it's a living structure constantly reshaped by dark energy's push and gravity's pull. Simulations show how slight density fluctuations after the Big Bang snowballed into today's intricate web, with Laniakea being just one ripple in this expanding fabric. The same forces that mold raindrops into rivers mold galaxies into superclusters because at its core, the universe is a story of flow, of matter finding its path through an ever-evolving landscape. This perspective transforms how we see our place in the cosmos. Earth isn't just orbiting a star in a galaxy. It's a speck within a supercluster that's itself a brushstroke in a masterpiece spanning 93 billion light-years. And just as neurons give rise to consciousness, perhaps these galaxy-scale networks are threads in a grander pattern we've only begun to decipher. After all, if the universe organizes itself like a brain, what other symmetries might we find hidden in its depths? Imagine standing on the banks of a vast, slow-moving river. Except instead of water, this current is made of galaxies, thousands upon thousands of them, all drifting in the same direction like celestial leaves caught in a gentle cosmic breeze. This is the mesmerizing flow within Laniakea, where entire galaxies glide along invisible gravitational highways, drawn toward the Great Attractor like iron filings pulled by a magnet. But what's truly fascinating is how this motion defies the universe's expansion, creating a paradox of movement where some galaxies race apart while others stream together in synchronized harmony. To understand this galactic traffic, picture two competing forces. First, there's the Hubble flow, the relentless outward expansion of space itself, stretching galaxies apart like raisins in rising dough. This is the universe's baseline rhythm, driven by dark energy's mysterious push. But superimposed on this is something far more intimate, the gravitational ballet of Laniakea, where galaxies don't just move apart. They're tugged sideways by the immense mass of the supercluster, sliding along filaments like beads on a string. The result, a celestial tug of war where expansion and gravity dance in intricate counterpoint. Fluid dynamics offers a surprising analogy. Think of Laniakea's motion like water swirling toward a drain. Galaxies closest to the Great Attractor fall faster, while those farther out move more slowly, creating a gradient of velocity akin to water accelerating as it nears a plug hole. But unlike a simple vortex, this flow is braided galaxies converge from multiple filaments, their paths twisting around voids in a delicate cosmic choreography. Simulations reveal these streams with startling clarity, showing how galaxies might start in different clusters but eventually merge into shared currents, all destined for the same gravitational basin. What's startling is the sheer slowness of it all. While individual galaxies zip through space at hundreds of kilometers per second, the supercluster's flow unfolds over epochs. Our Milky Way, for instance, won't reach the Great Attractor for tens of billions of years, if it ever does. That's because dark energy's influence is growing, stretching space faster than gravity can pull things together. In time, even Laniakea's mighty currents may be overcome, leaving future astronomers to wonder why ancient galaxies once moved in such strange, coordinated ways. Yet right now, we're privileged to witness this fleeting moment, a cosmic snapshot where gravity's grasp still shapes the large-scale universe. It's a reminder that motion in space isn't just about distance or speed. It's about stories written in the subtle deviations from expectation, the whispers of mass hidden behind veils of dust and darkness. Every galaxy's path is a clue, and together they sketch a map to the universe's most profound secrets. Defining where Laniakea ends and other superclusters begin isn't as simple as drawing borders on a cosmic map. These vast structures bleed into one another like watercolors on wet paper, their edges indistinct and ever-shifting. Take the Perseus-Pisces supercluster, Laniakea's neighbor, stretching hundreds of millions of light-years away. At first glance, the two appear separate, like distinct landmasses divided by an ocean of void. But peer closer, and you'll spot galaxies caught in a gravitational tug of war, their loyalties divided between these cosmic titans. Some streams of galaxies flow unmistakably toward Laniakea's Great Attractor, while others drift toward Perseus-Pisces' own dense hubs, creating a celestial no-man's land where classification becomes more art than science. This ambiguity has sparked heated debates among astronomers about how we should define superclusters in the first place. Traditionally, scientists relied on density thresholds. If enough galaxies clustered together in a region, they called it a supercluster. But Laniakea's discovery turned this approach on its head by introducing velocity flow as the defining feature. Suddenly, the question wasn't just where galaxies were, but where they were going. This shift revealed something profound. What we once saw as separate superclusters might actually be interconnected watersheds in a larger cosmic landscape. The controversy centers on a fundamental choice: do we categorize these structures based on their current positions or their shared gravitational destiny? Imagine trying to define continents by today's coastlines versus predicting where tectonic plates will carry them in a million years. Both approaches have merit. Density maps give us snapshots of the universe's current architecture, while velocity flows expose the deeper gravitational undercurrents shaping its future. The challenge is that these methods don't always agree, leaving regions like the border between Laniakea and Perseus Pisces caught in definitional limbo. Some researchers argue this ambiguity reveals a deeper truth, that superclusters aren't distinct entities so much as temporary density waves in the cosmic web. Simulations show these vast structures constantly forming and dissolving over billions of years, their boundaries reshaped by dark matter's invisible hand. The filaments connecting Laniakea to its neighbors might one day thicken into a single megastructure, or they might fray apart under dark energy's relentless push. What we're witnessing isn't just a classification challenge, it's a cosmic process unfolding in slow motion, reminding us that even the mightiest structures in the universe are fleeting patterns in an ever-changing tapestry. What makes this boundary dispute more than academic is what it reveals about gravity's reach. The overlapping influence zones between superclusters act like cosmic laboratories, showing how gravity operates over scales we once thought impossible. Galaxies near these borders experience competing pulls, their trajectories tracing delicate balance points in the universe's gravitational field. It's as if we're watching the universe's own version of plate tectonics, with supercluster-scale landmasses grinding past one another, their edges crumpling and merging in silent, slow-motion collisions. The resolution may lie in next-generation surveys like the Vera C. Rubin Observatory's legacy survey of space and time, which will map millions more galaxies with unprecedented precision. As our tools grow sharper, so too does our understanding of these cosmic borderlands, not as hard divisions, but as fluid transition zones where the universe reveals its most subtle and interconnected nature. Perhaps the most humbling lesson here is that our urge to neatly categorize the cosmos often bumps against reality's refusal to be boxed in, leaving us with beautiful, messy ambiguities that push science forward precisely because they resist easy answers. Watch the universe press play, and suddenly billions of years collapse into seconds, a cosmic ballet choreographed by gravity's invisible hand. Simulations reveal Laniakea's origin story not as a single explosive event, but as a slow, relentless gathering. Rewind to the universe's earliest epochs when matter wasn't yet stars or galaxies, just a nearly uniform sea of particles. But nearly is the key word. Tiny density fluctuations, smaller than 1 part in 100,000, created seeds around which everything would eventually cluster. These microscopic ripples, imprinted by quantum processes in the first fraction of a second after the Big Bang, became destiny's fingerprints, dark matter, that enigmatic substance outweighing normal matter 5-to-1, played the lead role. While regular matter interacted with light and radiation, slowing its growth, dark matter's ghostly indifference let it clump faster, forming vast, invisible scaffolds. Picture a city's steel skeleton erected before concrete is poured. Dark matter's filaments became the universe's framework, guiding galaxies toward intersections where they'd eventually bloom. Supercomputer visualizations show this process with eerie clarity. Rivers of dark matter flow and merge, their gravitational pull so potent that hydrogen gas, and eventually stars follows their lead like iron filings aligning to a magnet's field. As eons passed, these filaments thickened at their intersections, creating gravitational wells so deep they became supercluster hubs. The Great Attractor emerged as one such node, growing fat on a diet of infalling galaxies. Meanwhile, the voids between filaments stretched emptier, their matter siphoned away by the growing web. What's astonishing is the timescale. Laniakea didn't snap into shape overnight. It took over 13 billion years of galaxies sliding along dark matter's highways, drawn toward ever larger gatherings before the supercluster reached its current majesty. But the story doesn't end here. Fast forward to the universe's future, and Laniakea's fate hinges on a cosmic tug-of-war. On one side, gravity continues pulling our supercluster toward an even grander, meeting the eventual collision with the Shapley supercluster, the most massive structure in our cosmic neighborhood. Picture two immense whirlpools in space slowly spiraling toward each other. Yet opposing this is dark energy's relentless push, accelerating the universe's expansion. Over trillion-year timescales, this force may tear galaxies apart faster than gravity can gather them, leaving Laniakea's grand design to fade like a sandcastle at high tide. What simulations teach us is that we're witnessing just one frame in a cosmic film still playing. The same forces that built Laniakea will one day dismantle it, reminding us that even the universe's mightiest structures are temporary, ripples in spacetime's pond, beautiful precisely because they don't last. Every galaxy, star, and speck of dust we see in Laniakea amounts to barely a tenth of its true mass, the rest an invisible giant pulling the strings dark matter. This mysterious substance doesn't emit, absorb, or reflect light, yet its gravitational grip is so powerful it dictates how superclusters form and move. Think of it as the universe's hidden scaffolding. While ordinary matter builds the visible structures, dark matter's unseen architecture determines where those structures will rise and how they'll interconnect. One of the most compelling clues to dark matter's presence comes from gravitational lensing, nature's own magnifying glass. When light from distant galaxies travels through Laniakea, the supercluster's immense gravity bends its path, distorting the galaxy's shape like a funhouse mirror. By studying these distortions, astronomers can map the invisible mass causing them. Strong lensing creates dramatic effects, multiple images of a single galaxy or stretched arcs of light, but weak lensing is even more revealing for superclusters. Here, the distortions are subtler, like a faint ripple in a pond. Measuring thousands of these tiny bends across wide field surveys allows scientists to reconstruct dark matter's distribution with astonishing precision, revealing how its filaments thread through Laniakea's vast expanse. Different tools capture different facets of this shadowy framework. Weak lensing surveys, like those from the Subaru telescope or the upcoming Euclid space mission, excel at tracing dark matter's large-scale structure. They've shown that Laniakea's densest hubs align with regions where lensing is strongest, proof that galaxies congregate where dark matter's pull is most intense. Meanwhile, X-ray observations of hot gas trapped in galaxy clusters reveal how dark matter's gravity heats interstellar material to millions of degrees, creating glowing halos that indirectly trace its presence. Even the motions of galaxies themselves act as cosmic probes. Their peculiar velocities betray the tug of unseen mass, much like leaves swirling in a river reveal hidden currents beneath the surface. What's striking is how these methods converge on the same conclusion. Whether we're measuring bent light, scorching gas, or wayward galaxies, the story is consistent. Dark matter isn't just sprinkled randomly through Laniakea. It forms an intricate web with dense knots at supercluster intersections and tendrils stretching across voids. This hidden skeleton doesn't merely accompany visible matter. It predates it, providing the gravitational blueprint that guided ordinary matter into the luminous structures we see today. Without dark matter's influence, galaxies would be scattered thinly across space, never gathering into the majestic superclusters that define the cosmos's large-scale structure. Yet for all we've pieced together, dark matter remains an enigma. We've mapped its gravitational shadow, but its true nature, whether it's an undiscovered particle or something even more exotic, still eludes us. Every lensing distortion, every anomalous galactic motion is a breadcrumb leading deeper into the mystery. And as we follow those crumbs, we're not just uncovering the secrets of Laniakea. We're peeling back the veil on the universe's most fundamental architecture, one invisible thread at a time. The discovery of Laniakea didn't just rewrite astronomy textbooks, it sent ripples through human culture, reshaping how we see our place in the cosmos. Indigenous navigators, modern artists, and philosophers alike have found profound meaning in this galactic tapestry, each interpreting its vastness through their own lens. Take the Polynesian voyagers who crossed thousands of kilometers of open ocean using nothing but the stars. Their celestial maps weren't just practical tools, they were living narratives connecting sky and earth. The Maori concept of Wakapapa, a genealogy linking all existence, mirrors Laniakea's interconnected filaments in ways that feel almost prophetic. To these navigators, the universe was never a collection of isolated objects but a flowing network of relationships, an intuition modern science is only now catching up to. Contemporary artists have transformed supercluster data into stunning visual metaphors. Team Lab's immersive digital installations stretch Laniakea's filaments across gallery walls, letting visitors walk through scaled-down galactic streams. Astrophotographer Andrew Kuchling overlays supercluster maps onto desert landscapes, blending terrestrial and cosmic scales. These creations do more than dazzle. They make the invisible architecture of our universe tactile, transforming abstract data into emotional experiences. One particularly striking piece, Laniakea's Embrace by multimedia artist Ryoji Aikta, translates galactic velocities into pulsing sound waves, allowing audiences to literally hear the supercluster's gravitational currents. Such works reveal how art bridges the gap between scientific understanding and visceral awe, helping us feel what equations alone cannot convey. Philosophically, Laniakea has become a Rorschach test for humanity's cosmic identity. Some thinkers see our supercluster as humbling proof that even galaxies are mere specks in a grander scheme, what theologian Thomas Berry called the universe story. Others find paradoxical comfort in its fractal patterns, noting how neural networks and galactic webs echo one another. This resemblance has sparked bold conjectures about consciousness and cosmology, with some theorists proposing that self-similar structures at vastly different scales might hint at deeper universal principles. While such ideas remain speculative, they illustrate how Laniakea has become a canvas for our deepest existential musings. Perhaps the most profound cultural shift lies in how Laniakea redefines home. For centuries, humans saw Earth as the center of existence, then our solar system, then the Milky Way. Now we understand our address stretches further. We're citizens of a supercluster, temporary residents in a gravitational metropolis that itself is drifting toward some unseen destination. This expanded perspective mirrors the Copernican revolution, but with a crucial difference. Instead of displacing us from the center, it reveals our embeddedness in an animate, dynamic cosmos. Contemporary indigenous astronomers like those from the Maori and Navajo traditions have noted with wry amusement how Western science is finally converging with ancestral worldviews that always saw celestial patterns as living connections rather than isolated points of light. The most poetic resonance might be Laniakea's namesake heritage. The Hawaiian term meaning immeasurable heaven wasn't chosen randomly. It consciously honors Polynesia's star-guided legacy while inviting all cultures to see themselves within this new cosmic map. As we grapple with climate crises and geopolitical fractures, Laniakea offers a potent reminder. Borders are human inventions, but gravity is universal. Every culture's stories, from Maori creation chants to Greek mythology's celestial dramas, become interconnected threads in this supercluster spanning narrative. In an era where we can simultaneously feel more connected and more isolated than ever, Laniakea's silent, stately dance provides something rare, a sense of belonging writ large across the heavens themselves. Placing Laniakea on a cosmic scale reveals just how extraordinary and strange our supercluster truly is. Stack it against the Shapley supercluster, currently the heavyweight champion of our observable universe, and the differences become striking. Shapley, located about 650 million light-years away, packs a staggering mass around 10,000 times that of the Milky Way into a relatively compact core of galaxy clusters. It's like comparing a dense city skyline to Laniakea's sprawling suburbs. While Shapley's gravity dominates its region, warping space-time so severely that it pulls entire superclusters toward it, Laniakea's structure is more fluid, defined not by a single dense core, but by an intricate web of filaments stretching across a volume 5 times larger. Then there's the Hercules supercluster, another titan in this cosmic lineup. Hercules stands out for its peculiar shape, a long, flattened ribbon of galaxies spanning nearly 300 million light-years. Unlike Laniakea's radial flow toward the Great Attractor, Hercules appears more chaotic, with galaxies moving in seemingly discordant directions. Some astronomers speculate this could be evidence of a past collision with another supercluster, leaving its gravitational fabric permanently warped. It's a reminder that these structures aren't static, they're dynamic, evolving entities shaped by ancient cosmic violence. What truly sets Laniakea apart isn't just its size or mass, it's our front row seat to its dynamics. Because we're embedded within it, we can map its flows with precision impossible for distant superclusters. This proximity reveals subtle details, like the way galaxies nearer to the Great Attractor move faster than those on the outskirts, tracing a gravitational gradient invisible in other systems. Laniakea also offers a rare testbed for studying dark matter's role. Its filaments act like cosmic way stations, letting astronomers measure how invisible mass bends light and steers galaxies. But the most compelling reason to study Laniakea lies in its humbling normalcy. Unlike Shapley's extreme density or Hercules' odd kinematics, our supercluster represents a middle ground, a Goldilocks structure that's neither too massive nor too sparse. That makes it a Rosetta Stone for understanding the universe's large-scale architecture. If we can decode how Laniakea formed and behaves, we're one step closer to unraveling the rules governing all superclusters and perhaps the cosmos itself. Our Milky Way isn't just any galaxy in Laniakea, it's a suburban dweller on the supercluster's fringes, orbiting the gravitational metropolis from a quiet corner. Picture a spiraling island of 400 billion stars floating within a small galactic collective called the local group. This humble neighborhood includes about 50 galaxies, most of them dwarfs huddling close to two titans, our Milky Way and the Andromeda Galaxy. What's fascinating is how this local dynamic mirrors Laniakea's grand structure in miniature. Just as Laniakea's galaxies stream toward the Great Attractor, our local group has its own gravitational dance, with Andromeda and the Milky Way hurtling toward each other at 113 kilometers per second, destined to collide in about 4.5 billion years. When they merge, they'll form a colossal new galaxy astronomers whimsically call Milkdromeda, a beacon shining bright in Laniakea's future. But the Milky Way isn't the only celebrity in this cosmic census. Shift your gaze 22 million light-years toward the heart of Laniakea, and you'll encounter the Virgo cluster, a bustling hub of over 2,000 galaxies. This dense urban center of the supercluster exerts a gravitational pull so strong it's slowing down our local group's journey toward the Great Attractor, like a cosmic traffic jam. Virgo's core is a spectacle of extremes, galaxies crammed so tight they occasionally rip each other apart, their stars strewn across space in luminous tidal tails. At its center lies the monstrous galaxy Messier 87, home to the first black hole ever photographed, a 6.5 billion solar mass behemoth that's the gravitational anchor for this entire district. Now zoom out slightly to meet the Fornax cluster, another key player in Laniakea's southern reaches. While smaller than Virgo, Fornax has a peculiar trait: it's slowly disintegrating. Observations show galaxies leaking from its edges, tugged away by the Great Attractor's irresistible pull. This slow-motion breakup reveals how even tightly bound clusters aren't immune to the supercluster's overarching flow. Meanwhile, on Laniakea's opposite flank, the Antlia Wall, a sprawling filament of galaxies acts like a cosmic freeway, funneling galaxies toward denser regions in a river of starlight. Each of these residents tells a story about Laniakea's structure and evolution. The Milky Way's quiet suburban life, Virgo's dense urban core, and Fornax's gradual dissolution all showcase different fates galaxies face within the supercluster. And beyond the well-known names lie countless dwarf galaxies, often overlooked but crucial to understanding the cosmic web. Take the Sagittarius dwarf, currently being cannibalized by the Milky Way, or the Large Magellanic Cloud, a satellite galaxy orbiting ours with such vigor it's warping our galaxy's disk. These smaller players are like cosmic plankton, feeding larger galaxies and tracing the gravitational currents that shape Laniakea's hidden architecture. What's startling is how much motion hides behind the seemingly static night sky. While we perceive constellations as fixed, these stars are just our immediate neighbors in a galaxy that's itself racing through space. The entire local group is being pulled toward Virgo, which in turn is falling toward the Great Attractor, which is likely drifting toward the Shapley supercluster beyond. It's a cascade of motion, each scale nested within a larger one, all unfolding at speeds that defy human intuition. The universe isn't just expanding, it's flowing, and we're caught in its currents, passengers on a voyage set in motion billions of years before Earth even formed. Within Laniakea, galaxies don't drift aimlessly, they move in a synchronized celestial ballet, orchestrated by gravity's unrelenting pull. Picture a giant pendulum wave where hundreds of swinging weights create rippling patterns. Each pendulum moves independently, yet together they form a harmonious flow. That's how galaxies behave here. While each follows its own path, their collective motion reveals the supercluster's hidden rhythms, all tracing the gravitational contours of dark matter's invisible scaffold. Take our Milky Way's trajectory. We're not just speeding toward the Great Attractor in a straight line. Our path resembles a spiraling descent, like water circling a drain. That's because gravity doesn't tug uniformly. Nearby galaxy clusters like Virgo exert their own influence, deflecting our course subtly. It's a cosmic game of pinball where every massive object we pass nudges us slightly, adding complexity to our journey. Meanwhile, galaxies closer to Laniakea's core whip around faster, obeying the same orbital rules as planets in a solar system, just scaled up by a factor of billions. Those near the Great Attractor complete their orbits every few 100 million years, while outlying galaxies like ours take tens of billions of years to complete a single loop. The most mesmerizing motion happens along Laniakea's filaments. Here, galaxies stream single file like commuters on a cosmic highway, sliding toward dense nodes at speeds exceeding 1,000 kilometers per second. Yet even this flow isn't chaotic, it follows predictable patterns, with galaxies nearer the filament's edges moving slower than those at the center, much like how water flows faster mid-river than near its banks. Occasionally, galaxies collide in spectacular mergers, their stars and gas shredded into luminous tails, but most glide past one another, their vast distances preventing direct hits. What's startling is how this dance defies the universe's expansion. While dark energy pushes most galaxies apart, Laniakea's members resist, bound by gravity's intimate grip. Over time, however, even this embrace may loosen. Currents that now flow together could one day be torn asunder, leaving only echoes of a once mighty supercluster. For now, though, we're caught in the sway of a gravitational waltz that began billions of years ago, a fleeting performance in the cosmos' grand theater. The universe's oldest light holds secrets about Laniakea's immense gravity. The cosmic microwave background, that faint afterglow from the Big Bang, carries faint temperature variations, and some of those whispers in the static reveal where superclusters like ours tug on spacetime itself. This phenomenon is called the integrated Sachs-Wolf effect, and it works like a cosmic fingerprint. As light from the CMB travels through supercluster-scale gravitational wells, it gains energy falling in but loses less climbing out due to dark energy's accelerating expansion. The result, slight warm spots where photons gained energy passing through massive structures, and cool patches where they expended extra effort escaping gravitational valleys. Think of it like rolling a marble over a bumpy surface. The marble speeds up downhill but slows climbing up. Now imagine that surface spans 500 million light-years, with Laniakea as one of the largest bumps. Satellite missions like Planck have mapped these minute temperature shifts with exquisite precision, revealing a subtle but unmistakable warm blob aligned with our supercluster's position. It's as if the universe's baby photo taken when it was just 380,000 years old still bears the shadow of structures that wouldn't form for billions of years. What's astonishing is how faint these signals are, temperature deviations of mere millionths of a degree. Detecting them required averaging data from thousands of galaxy clusters, teasing out patterns hidden in noise. But the payoff is extraordinary. These observations confirm that Laniakea isn't just a chance grouping of galaxies. Its gravity bends the fabric of the universe deeply enough to leave scars on radiation that's been traveling since the cosmos was a swirling plasma. The implications stretch far beyond mapping. Since dark matter dominates Laniakea's gravitational pull, these CMB distortions help quantify how much invisible mass truly threads through the supercluster. They also offer clues about dark energy's behavior, the reason photons lose less energy climbing out of gravitational wells than they gain falling in. Without dark energy's repulsive push, the effect would cancel out entirely. In this way, Laniakea isn't just a structure we study. It's become a laboratory for probing the universe's most enigmatic forces, using ancient light as both microscope and messenger. Yet mysteries remain. Some regions show stronger ISW signals than expected, hinting at additional mass or peculiar flows we've yet to account for. Others align poorly with visible matter maps, suggesting unseen structures lurk behind the Milky Way's veil. Every discrepancy is a breadcrumb leading us deeper into the dark universe's hidden architecture, one temperature fluctuation at a time. Laniakea's story begins not with a bang but with a whisper, a quantum flicker in the newborn universe. In the first trillionth of a second after the Big Bang, microscopic ripples in spacetime's fabric, no larger than a proton, sowed the seeds for everything we see today. These fluctuations, imprinted by quantum chaos during cosmic inflation, were the universe's first brushstrokes. Where matter clustered slightly denser, gravity gained a foothold, amplifying those tiny overdensities over billions of years. Dark matter, silent and invisible, led the charge, its particles immune to radiation's push, allowing it to clump into vast tendrils long before ordinary matter could catch up. Picture an invisible spider spinning a web in the dark, its threads only revealed when gas and stars later lit up along its strands. For Laniakea, the turning point came around 2 billion years after the Big Bang, when the first protofilaments began condensing from the cosmic fog. Hydrogen gas, cooled by the expanding universe, pooled in dark matter's gravitational wells, igniting the first galaxies like fireflies in a valley. Over eons, these galaxies danced along the filaments, pulled toward intersections where clusters would blaze into being. The Great Attractor emerged as one such nexus, a gravitational pit so deep it became a galactic whirlpool, drawing in everything within its reach. Simulations show this growth wasn't smooth but punctuated by violent mergers. Smaller clusters smashed together like celestial traffic collisions, their gas heated to millions of degrees, while dark matter halos passed through one another like ghost ships in the night. Yet this majestic assembly faces two possible futures, hinging on a cosmic tug-of-war. On one side, gravity strives to pull Laniakea tighter galaxies streaming toward the Great Attractor, could eventually merge into a single hypermassive cluster, a glittering megalopolis in an otherwise emptying universe. But opposing this is dark energy's relentless push, stretching space itself faster than gravity can gather matter. If dark energy strengthens over time, a scenario called the Big Rip, even superclusters won't survive. First, Laniakea's outer galaxies would vanish beyond the cosmic horizon, their light stretched to invisibility. Then, the filaments themselves would fray, galaxies torn apart as the space between stars expands faster than gravity's grasp. Finally, in a feverish finale, atoms themselves would be ripped asunder, the universe dissolving into a sea of disconnected particles. Between these extremes lies a middle path, the heat-death scenario where dark energy's expansion is gentler but inexorable. Here, Laniakea would collapse inward, merging with the Shapley supercluster in 100 billion years, only to grow isolated as the accelerating universe carries all other structures beyond reach. Galaxies would burn through their star-forming gas, their lights winking out one by one until only black holes remain, slowly evaporating into Hawking radiation over incomprehensible timescales. What's humbling is that Laniakea's fate isn't unique. It's a microcosm of the universe's own life cycle. The same quantum seeds that birthed our supercluster also predetermined its end, written into the cosmos's opening line. Whether it ends in fire or ice, in a grand collapse or a silent fade, its story reminds us that even the mightiest structures are fleeting patterns in an ever-changing tapestry, their existence a brief spark between the darkness of the past and the void of the future. Not everyone agrees that Laniakea deserves its title as a distinct supercluster. Some astronomers argue it might just be a temporary density fluctuation in the cosmic web, a ripple in spacetime's fabric rather than a true structural entity. At the heart of this debate is a fundamental question: how do we define what makes a supercluster in the first place? Traditional astronomy classifies superclusters based on galaxy density, regions where clusters pack unusually close together. By that standard, Laniakea fits the bill, but critics point out that gravity's reach extends far beyond visible matter, creating overlapping zones of influence. Harvard astrophysicist Dr. Margaret Geller likens superclusters to weather systems in a cosmic storm, constantly shifting, merging, and dissolving. From this perspective, Laniakea's boundaries may be arbitrary. Its galaxies, no more bound to each other than clouds in a passing front, are destined to stay together. The controversy deepens when we examine the Great Attractor. While its gravitational pull is undeniable, researchers dispute what actually lies at its core. Some contend it's not a singular anomaly but a confluence of multiple dense regions. The Norma cluster combined with the Centaurus cluster and hidden mass concentrations behind the Milky Way's dust. Others, like University of Hawaii's Dr. R. Brent Tully, who co-discovered Laniakea, maintain that velocity mappings prove its coherence as a unified flow system. Compounding the confusion are rival mapping methods. The density peak approach identifies superclusters as mountains in the galaxy distribution, while the velocity flow method prioritizes shared motion, the technique that revealed Laniakea. These frameworks don't always align. For instance, the Perseus-Pisces supercluster appears separate in density maps but blends into Laniakea's flows, creating classification headaches. Perhaps most provocative is the end of greatness hypothesis, the idea that beyond a certain scale, the universe has no true structures, just statistical clustering. If correct, Laniakea would be a fleeting pattern in chaos, not a lasting cosmic landmark. Yet amidst these debates, one truth endures: Whether temporary or permanent, Laniakea offers an unprecedented window into how gravity weaves the universe's largest tapestries, threads of dark matter and starlight stretching farther than we ever imagined. Even as we marvel at Laniakea's vastness, new telescopes are poised to peel back its remaining mysteries, revealing hidden dimensions of this cosmic giant we've only begun to trace. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, will soon unleash the most comprehensive celestial census ever attempted. Imagine a camera the size of a small car, capturing ultra-wide field images of the southern sky every few nights for a decade. This relentless scanning won't just record static snapshots, it'll track subtle changes in billions of galaxies' brightness and positions, creating a time-lapse movie of the cosmos. For Laniakea, this means mapping its galactic currents with unprecedented precision, potentially uncovering hidden tributaries or even entirely new filamentary branches currently obscured by dust. Meanwhile, the Euclid Space Telescope approaches the puzzle from another angle. Orbiting beyond the Moon's shadow, this European Space Agency mission will chart the universe's large-scale structure in 3 dimensions, using gravitational lensing to expose dark matter's invisible hand. While LSST scans from Earth with breathtaking breadth, Euclid's infrared eyes peer deeper, measuring how dark matter distorts the light from 15 billion galaxies, many within Laniakea's sprawling domain. Together, these projects could resolve long-standing debates about our superclusters' true extent. Are its borders truly where we've drawn them, or does Laniakea feather into neighboring structures like Perseus Pisces in ways our current maps can't capture? But the revelations won't stop at mere cartography. Spectroscopic instruments like the Dark Energy Spectroscopic Instrument, or DESI, are decoding galaxies' motions across 10 million light-years with pinpoint accuracy. These velocity maps could reveal if Laniakea harbors unexpected substructures, perhaps smaller attractors hidden within its flow, like eddies in a galactic river. There's even tantalizing speculation about missing mass in the supercluster's outskirts, where galaxies move faster than visible matter alone can explain. Some theorists wonder if this anomaly hints at exotic physics, dark matter behaving differently on supercluster scales, or even undiscovered gravitational phenomena. The most profound discoveries may come from peering beyond Laniakea altogether. Upcoming surveys could confirm whether our supercluster is merely one thread in an even grander tapestry, the South Pole Wall, a filamentary structure spanning over 1.4 billion light-years. If confirmed as a continuous entity, it would dethrone Laniakea as the reigning giant in our cosmic neighborhood, relegating our supercluster to a branch on this colossal cosmic tree. Such findings wouldn't diminish Laniakea's significance, but contextualize it within a hierarchy of structures we're only beginning to perceive. What makes this era of exploration thrilling isn't just better instruments, it's the convergence of multiple disciplines. Cosmologists now combine galaxy surveys with neutrinos and gravitational wave data, piecing together a multisensory portrait of the universe's scaffolding. Imagine astronomers of the future overlaying Laniakea's dark matter maps with signals from next-generation gravitational wave observatories, tracing how collisions of supermassive black holes echo through the supercluster's voids and nodes. We're not just mapping static terrain anymore, we're learning to read the cosmos as a dynamic, evolving entity, with Laniakea as our nearest and richest case study. Every new dataset is another stitch in the tapestry, revealing how the universe weaves its grandest designs. Gazing up at the night sky with nothing but binoculars or a small telescope, you'd never guess you're looking at the outer edges of a 500 million light-year cosmic metropolis. But with the right know-how, you can trace the contours of Laniakea's doorstep from your backyard. Start by locating the Virgo cluster, the bustling downtown of our supercluster. On spring evenings, find the constellation Virgo high in the southern sky. look for its brightest star Spica, then star hop northwest to a hazy patch near the star Porrima. That faint glow isn't a cloud, it's the combined light of over 2,000 galaxies, the closest major knot in Laniakea's web. Even a modest 6-inch telescope will reveal its brightest members, like the giant elliptical galaxy Messier 87, home to that famous black hole photographed in 2019. For a real challenge, try spotting the Great Attractor's neighborhood, though don't expect to see the monster itself. Our galaxy's dust blocks visible light, but you can frame its general location. From the southern hemisphere, locate the constellation Norma near Scorpius's tail. The Norma cluster lurks here, one of the Great Attractor's primary mass concentrations. While its galaxies are too faint for small scopes, you'll be training your eyes on the gravitational epicenter pulling our entire galactic neighborhood. What's astonishing is how much of Laniakea's structure you can map with persistence. Follow the Hydra Centaurus supercluster by tracing a chain of galaxies stretching from the Centaurus, a radio galaxy, visible as a faint smudge through binoculars toward the Hydra cluster. These are the supercluster's southern filaments, backbone structures feeding galaxies toward the Great Attractor like cosmic conveyor belts. Seasoned observers with larger telescopes can even glimpse the outskirts of the Pavo in Dust supercluster, another tributary in Laniakea's flow. You don't need expensive gear to contribute to real science either. Projects like Galaxy Zoo invite amateur astronomers to help classify galaxies in supercluster surveys. By analyzing images from robotic telescopes, you might spot previously unnoticed dwarf galaxies or tidal streams, crumbs leading to hidden dark matter concentrations. Other initiatives like the Backyard Worlds program let volunteers scour infrared data for cool stars or brown dwarfs that could be drifting through Laniakea's fringes. Every submitted observation helps refine our 3D maps of this colossal structure. For those craving hands-on adventure, try sketching galaxy fields the old-fashioned way. Plotting positions of faint smudges across multiple nights reveals their motions relative to background stars, the same technique early astronomers used to discover galactic flows. Modern apps like Stellarium now overlay supercluster boundaries, turning casual stargazing into cosmic cartography. There's a thrill in knowing that while your eyes take minutes to adjust to the dark, the light hitting your retina has traveled millions of years across Laniakea's vast networks, a personal connection to the grand architecture of our universe, no professional observatory required. Laniakea doesn't just challenge our sense of scale, it reshapes our very understanding of where and what we are in the universe. For centuries, humans saw Earth as the center of all things, then the solar system, then the Milky Way. Now we find ourselves adrift in a supercluster so vast it defies intuition, one thread in a cosmic web stretching beyond comprehension. This realization carries a double edge. It's humbling to grasp how small we are, yet strangely empowering to recognize how deeply connected we are to something so grand. The ancient philosophical question, why are we here, gains new dimensions when framed against Laniakea's unimaginable expanse. Are we mere accidents of gravity and chemistry, or does our ability to map and marvel at these structures hint at something more? The cosmic brain metaphor captures this duality beautifully. When astronomers first noted how Laniakea's filaments resemble neural pathways, it sparked awe and skepticism. Scientifically, the comparison holds merit. Both systems optimize efficiency through dense hubs and long-range connections, minimizing energy use while maximizing information flow. Galaxies cluster where gravitational traffic is heaviest, just as neurons wire together along frequently used thought pathways. Even the voids between supercluster filaments mirror the silent spaces between firing brain cells. But there's a crucial distinction. While brains process information deliberately, Laniakea's structure emerges from mindless physical laws. The resemblance is poetic, not literal, a reminder that nature often repeats its patterns across scales without deeper meaning. Yet dismissing the metaphor entirely misses its value. For millennia, humans have used familiar frameworks to comprehend the incomprehensible. Polynesian navigators saw constellations as celestial canoes. Ancient Greeks imagined gods threading the sky. Today, we use neural networks as a lens to decipher cosmic webs. These analogies aren't just shortcuts, they're bridges between the known and unknown, tools to spark curiosity that rigorous science can later refine. When a biologist studies a neuron and an astronomer maps a galactic filament, their shared language of connections and hubs fosters interdisciplinary breakthroughs, proving that even imperfect metaphors can guide discovery. Existentially, Laniakea offers a paradox. Its scale could make human existence feel insignificant, a fleeting spark in an indifferent universe. But another perspective emerges. We're matter that has become conscious of itself, capable of tracing our lineage back to the quantum ripples that birthed superclusters. In that light, we're not just inhabitants of the cosmos, we're its way of understanding itself. Indigenous cosmologies have long embraced this idea. The Maori concept of Wakapapa, for instance, views all existence as an unbroken genealogical chain linking stars, land, and people. Modern physics echoes this, showing how the carbon in our bodies was forged in dying stars, how the gravity we study shaped the galaxies we admire. Perhaps the most profound implication lies in Laniakea's impermanence. Like all superclusters, it's a temporary arrangement, a snapshot in a billion-year dance of gravity and expansion. That transience mirrors our own fleeting lives, yet also connects us to something timeless. Every galaxy we map, every dark matter thread we trace, is part of a story that began before Earth formed and will continue long after it's gone. To ponder Laniakea isn't just to study the universe, it's to find our place in its unfolding narrative, a single note in a symphony written in the language of physics but heard in the human heart. Imagine a civilization orbiting a star near the Great Attractor, their night sky dominated by the glow of thousands of densely packed galaxies. For them, mapping the cosmos wouldn't involve searching for distant landmarks. They'd swim in a sea of light, tracing celestial currents the way Polynesian navigators read ocean swells. Their coordinate system might center on the gravitational epicenter they inhabit, with radial lines extending along filamentary highways toward outlying voids. Distance markers could be calibrated by the blue shift of infalling galaxies, their motion toward the attractor creating a natural velocity-based ruler. Now contrast this with a planet orbiting a lonely galaxy in Laniakea's outer fringes. Their astronomers would face the opposite challenge, a sky sparsely dotted with galactic neighbors, where the Great Attractor appears as a faint, mysterious region pulling everything toward it. Their star charts might resemble desert nomads' maps' emphasis on rare oases of light, with vast empty spaces between. Instead of using galaxy clusters as reference points, they could rely on the peculiar motion of their own galaxy as it streams toward the supercluster's heart, turning their home's trajectory into the ultimate compass needle. Dwellers within the Norma cluster, a dense knot near the Great Attractor's core, would experience celestial navigation on hard mode. With galaxies packed so tightly that collisions are frequent, their night sky might resemble a glittering avalanche of merging spirals and ellipticals. Traditional constellations would be useless, the stellar patterns reshuffled every few million years by gravitational chaos. Instead, their coordinate system could be dynamic, updating in real time as nearby galaxies jostle for position, with AI constantly recalculating their place in the ever-shifting galactic metropolis. What about a civilization living in one of Laniakea's barren voids? For them, the few visible galaxies would appear unnaturally bright against the darkness, like lighthouses in a cosmic ocean. Their star maps might treat these isolated galaxies as sacred waypoints, with navigation relying on precise redshift measurements to gauge depth in an otherwise featureless expanse. The concept of a supercluster could be purely theoretical, an abstract mathematical construct rather than a visible structure. making their eventual realization of being part of Laniakea's web all the more shocking. The most intriguing perspective might come from a species whose planet orbits a galaxy caught in the borderlands between Laniakea and the Perseus-Pisces supercluster. Their astronomers would witness a celestial tug-of-war first, and some galaxies moving toward one gravitational giant, others toward its rival. Their coordinate system could be bifurcated, with two competing reference frames depending on which supercluster's influence dominates a particular region of space. This duality might even shape their cosmology, leading to philosophical traditions that embrace binary forces as fundamental to universal order. Regardless of location, all these civilizations would share one realization: their view of the cosmos isn't universal but profoundly local. Just as Earth's ancient cultures developed unique constellations based on their latitude and landscape, extraterrestrial astronomers would craft star maps reflecting their specific perch in Laniakea's grand architecture. The true masterpiece would emerge only when these disparate perspectives are combined, revealing that every coordinate system, no matter how alien, is just a fragment of the supercluster's deeper harmony. Gravitational waves, the ripples in space-time from colliding black holes, don't just tell us about isolated cosmic crashes. They carry whispers of the larger structures they pass through, including the vast gravitational well of Laniakea. When two black holes spiral into each other, the waves they emit don't travel through empty space. They traverse a universe sculpted by supercluster-scale gravity, where space-time itself is subtly warped by the mass of hundreds of thousands of galaxies. Picture tossing a pebble into a pond, but instead of smooth water, the ripples must navigate submerged boulders and currents. Laniakea's gravitational field acts like those hidden obstacles, bending and stretching the waves on their journey to Earth. This distortion isn't just theoretical. Advanced detectors like LIGO and Virgo are now sensitive enough to spot minute shifts in gravitational wave signals that reveal their passage through dense cosmic environments. For example, waves originating from collisions near the Great Attractor's core travel through stronger gravitational gradients than those from Laniakea's outskirts. The result, a detectable smearing effect where the wave's frequency gets slightly nudged as it climbs out of the supercluster's deep gravitational well. It's akin to hearing an echo change pitch as it bounces off a mountain, except here, the mountain is made of dark matter and galaxies, and the echo is a space-time ripple from a billion-year-old collision. But the influence goes both ways. Just as Laniakea shapes gravitational waves, the waves themselves can help map the supercluster's unseen mass. By analyzing how signals from multiple mergers are distorted along similar paths, astronomers can triangulate where dense dark matter filaments lie. Some researchers propose that future gravitational wave observatories, like the space-based LISA mission, could use this technique to chart Laniakea's hidden architecture with unprecedented precision, turning black hole collisions into cosmic sonar pings. The most tantalizing possibility involves echoes from supercluster-scale events. When supermassive black holes merge, a fate awaiting many galaxies in Laniakea's core, they emit gravitational waves so low frequency they're measured in years rather than seconds. These waves stretch and compress space-time across the entire supercluster, potentially causing minuscule, rhythmic shifts in the distances between galaxies. While we can't detect these yet, next-generation tools might one day measure how Laniakea rings like a colossal bell struck by black hole collisions, its vibrations revealing secrets about the universe's largest structures. What's truly revolutionary is the timescale. Gravitational waves from mergers we detect today began their journey when Laniakea's filaments were still assembling, carrying snapshots of a younger supercluster. By comparing these ancient signals with modern maps, we're effectively watching Laniakea's evolution in reverse, a cosmic time machine written in spacetime's tremors. Every ripple is more than a black hole's death knell. It's a messenger from the supercluster's past, whispering clues about how gravity weaves the universe's grandest tapestries. Step inside a virtual universe where galaxies stream past you like fireflies in the night, their trajectories painting luminous arcs across the void. This isn't science fiction, it's the cutting edge of cosmology, where virtual reality transforms raw data into visceral experiences. Scientists now strap on VR headsets to literally step inside supercomputer simulations of Laniakea, navigating its filamentary highways and gravitational whirlpools with motions as natural as turning your head. The latest immersive visualizations don't just show the supercluster, they let researchers feel its scale in a way flat screens never could. Imagine reaching out to touch the Milky Way's position on the cosmic web, then pivoting to watch hundreds of thousands of galaxies flowing toward the Great Attractor like water down a celestial drain. These simulations leverage breakthroughs in volumetric rendering and gravitational physics. Supercomputers crunch terabytes of redshift surveys and dark matter maps, converting numbers into three-dimensional landscapes where density gradients become tangible terrain. Dense galaxy clusters loom like mountains, while voids stretch into yawning chasms. The genius lies in how these tools handle scale. With a flick of the wrist, astronomers can zoom from a bird's-eye view of the entire supercluster down to individual galactic neighborhoods, all while real-time velocity vectors streak across their field of vision like cosmic wind vanes. Some systems even incorporate haptic feedback, allowing users to sense gravitational tides through subtle vibrations as they pass near massive clusters. What makes VR so revolutionary isn't just spectacle, it's scientific discovery. Traditional 2D projections often obscure crucial spatial relationships, like how filamentary threads twist around voids in helical patterns. In virtual reality, these complex geometries snap into clarity. Researchers at the University of Hawaii's Institute for Astronomy famously spotted previously hidden tributaries in Laniakea's structure simply by walking around a VR reconstruction and noticing gravitational gradients from new angles. Other teams use collaborative virtual spaces where avatars of scientists from different continents can gather inside the simulation, pointing out anomalies in real time as if examining a shared hologram. The public gets to ride along too. Planetariums worldwide now offer immersive Laniakea experiences, where audiences soar through the cosmic web in dome theaters equipped with motion tracking. Home users can explore scaled-down versions through apps like Space Engine, which stitches real astronomical data into procedurally generated universes. Educators are leveraging these tools to make cosmology tactile. Students don't just learn about superclusters, they navigate them, feeling the gravitational tug of dark matter as they fly toward the Great Attractor's hidden depths. Yet the most profound impact might be philosophical. Standing in VR amidst Laniakea's glittering expanse, with galaxies drifting past at scales the human mind struggles to comprehend, triggers what astronauts call the overview effect, a cognitive shift where theoretical knowledge becomes embodied understanding. You don't just know the Milky Way is a speck in the supercluster, you experience that fragility viscerally, floating in a sea of giants. This emotional resonance is why these simulations matter beyond academia. They're bridges between data and wonder, letting anyone with a headset grasp the universe's grandeur in a way words alone cannot convey. Emerging technologies promise even deeper immersion. Light field displays will soon eliminate VR motion sickness by perfectly mimicking how light behaves in real space. AI upscaling techniques are filling gaps in our Laniakea maps with plausible detail, while quantum computing simulations will model the supercluster's evolution with unprecedented accuracy. Some labs are experimenting with full-body haptic suits that let wearers feel the gravitational pull of passing galaxies as physical resistance, turning abstract astrophysics into something you can literally lean into. The irony is delicious. The same medium we use for fantasy games is now revealing fundamental truths about reality's fabric. every time a scientist reaches out in VR to trace a filament back to its source, or a student gasps at seeing the Milky Way's insignificance amid Laniakea's sprawl, we're witnessing more than technological progress. We're seeing humanity's oldest questions: where are we, and how does this all fit together, answered not with equations alone, but through experiences that engage our senses, our curiosity, and our awe. Standing back to take in Laniakea's full majesty, the numbers alone defy comprehension: 500 million light-years of woven galaxies, 100,000 galactic cities adrift in a web of dark matter, all bound by forces that sculpted the universe from its first whispers. Yet what lingers isn't just the staggering scale, it's the revelation that this cosmic metropolis, for all its grandeur, is but a single brushstroke in a far vaster canvas. We've spent centuries mapping coastlines and continents, only to look up and discover our true geography extends far beyond any atlas, threading through filaments of starlight older than Earth itself. Carl Sagan once asked us to consider the pale blue dot, our entire world reduced to a pixel in Voyager's farewell snapshot. But from Laniakea's vantage, even that perspective feels intimate. Here, entire galaxies become specks, their combined light barely a shimmer against the void. Yet there's a quiet poetry in knowing that the same forces guiding these galactic rivers also spun our planet into being. Every atom in our bodies was forged in stars now lost to time, their remnants scattered across the supercluster's expanse, cycling through new suns and worlds in an unbroken cosmic dance. What does it mean to call a place like this home? Not just a planet or a solar system or even a galaxy, but a gravitational archipelago spanning epochs. Perhaps it's this, that the universe's greatest gift is the ability to trace our lineage back to its grandest structures and forward to whatever wonders lie beyond. Laniakea won't last forever. Dark energy may one day tear its threads asunder, but for now, we're here to witness it, to map its currents, and to marvel at the fact that something as small as a human mind can hold something so impossibly large. So the next time you step outside under a clear night sky, remember, you're not just looking at stars, you're glimpsing the edge of a supercluster, your personal window into a story 13 billion years in the telling. And who knows what chapters remain? The universe has never stopped surprising us, and Laniakea is proof that the deeper we look, the more we find we're part of something far greater than we ever dreamed. The conversation doesn't end here, it's only just begun. What mysteries do you think hide in the cosmic web's next fold?